Welcome to the first episode of a new series called TypeScript Type Theory. In this series, we'll use TypeScript code to illustrate and help to explain ideas from type theory and logic. In the first episode today, we're going to start with Lambda expressions. Now, Lambda expressions were created by Alonzo Church in the 1930s as a way of trying to describe computable functions. I had actually planned to do a whole section of this video where I was writing on a digital whiteboard, but I had a lot of trouble getting my iPad screen to record properly. So maybe in the next video we'll get that sorted out. But for now, we're still stuck with just my voice and the code editor, and hopefully that will be enough. We'll start with the definition of a Lambda expression. And we can define it as one of three subtypes, either a free variable, which is, we'll see the definitions of each of these in a minute. So it's either a free variable, an application, or an abstraction. I've given examples down there of what these would look like in traditional mathematics notation. Free variable is just something like x or y. It is essentially a string that stands for some undetermined value. And an application is when you take one of those and you apply it to the other. Here we're applying x to y. And we call x we can call x the function and y the argument of the function. And we can also say that we pass y to x if we want to talk about it going from right to left. For abstraction, we have our special lambda symbol here, which is what the lambda calculus is named after. And this part here is called the parameter of the abstraction. And the part after the dot is called the body. Now you'll also notice these little circles here. This is a new notation I've introduced because I found it confusing to keep track of which variables were bound and which are free. Now, a bound variable is one that is falling under the scope of this parameter here. So over here, we see that x is just it's just an x. It has no lambda abstraction that is going over top of it, and so it doesn't have that little circle there. Whereas over here, this parameter is kind of binding to the x variable over here, and that we indicate with this little circle. Just is a visual aid to help keep everything straight, and it will also actually be useful when we're doing some substitution and whatnot to be able to check for which variables are bound and which variables are free. So let's see how we could implement that. So we're going to just call a variable a string. There's no reason to make it much more complicated than that. And a free variable is just a variable. But for a bound variable, we can use this neat feature that TypeScript has of string template literals, where you can actually check to see if this little circle is on the left-hand side of the string. And when we produce our bound variables, we'll make sure that they have that type. By the way, this circle is a Unicode character, so it's not something you'd be likely to just type if you're typing a variable name, and thus it's, I think, fairly safe that you're not going to accidentally type it. Plus, we're going to remove it anyways when we create our variable constructor function. Okay, this is just a predicate function to determine if something is a bound variable. If it's a string and it has a little circle at index 0, then we're going to call it a bound variable. And here's our variable constructor function. These are just overloads so that if we pass in different values for the second argument, which is the free argument, we're going to get the correct type from TypeScript. So it defaults to free if you don't pass in the second argument. It's going to replace all instances of that circle character with the empty string. And then if it is free, it will just return that string with the circles deleted. If it's not free, it will add the circle back in, and it does it using a template literal, which is going to give it the correct type that we want for our bound variables. And so you're going to get here your variable back. So for free variables, we can just use strings. So we're just going to define a bunch of free variables that we'll use later on in some of our examples. And then for a bound variable, we can use this constructor function. And if you check the type here, you can see that it has the correct type of string with in the template with the little circle next to it. All right, now that we can move on to defining our applications. So an application is, first of all, it has a role property here. This is going to be used when we're differentiating which syntax type we're dealing with. Is it an application or is it an abstraction? And then we've got function and argument. So that's like this is the thing that's being applied, the function, and this is what it's being applied to. And both of those can be arbitrary lambda expressions. They can be any lambda expression at all. The toString is just going to be what lets us print it out to the console. And now we have our constructor function. This was our type for application. Now we're going to have a thing which allows us to construct our application values. And this is, to make it easier to write, I'm going to take an array of lambdas rather than just taking 2. But we need at least 2, so we're going to throw an error if we get less than 2 in that array. And now this is how you construct a single application, like a non-nested application. You just simply take the first lambda and the second lambda as function and argument, and you put them here into your object, and then you return the whole thing. So what we're going to do it in an iterated way is we're just taking current equal to the first 2 arguments applied to this one applied to that one, and then for any I greater than 1, which is to say for the 3rd, 4th, 5th, and so on in the array, if there are any such, we will apply it to current and then set current equal to that. So essentially we're creating like a nesting of applications. And this way we can simply do something like this. We can do apply x, y, z dot toString and save that. And we should have our application there. If we want to do x, y, z, w, we can get the w there. Now, one thing to be aware of is by default, apply is associative to the left. So doing this is equivalent to doing a nested apply where I apply first x to y, and then I apply the next argument, and then I apply that whole thing, the x applied to y to z, and then the x applied to y and z to w. But if we want to do it in a different order, we have to explicitly add in a new apply call there. And then you'll see that it adds in the toString method, it adds in the brackets in the right places so that we get our right association there. So now we're applying z to w, and we're applying x to y, and then to z applied to w. Okay, so moving on to abstraction, we've got our 2 parts, our parameter and body. Now, a parameter is not actually a Lambda expression in and of itself. It's a part of a Lambda expression, and it's this bound variable. So that's important. And the Lambda, again, can be any Lambda expression. And we've got our toString function to translate it into a string. So now we're going to define this toString function now that we've got all our types defined. And basically, we don't need a toString function for variables because they are already strings. So for abstractions, we're going to put square brackets around it and use this Lambda symbol at the beginning, then the parameter, then a dot. So the dot separates the parameter and the body. And then we're going to just put the body turned into a string and then end with a square bracket. For our application, we're simply using smooth brackets to surround the argument and putting that together with the function. This, by the way, is just a way to ensure that we've covered all our cases. So we said that the argument of this has to either be an abstraction or an application. And if we had forgotten to cover one of those cases, like let's say we didn't have this last else if statement here, then we would see that their TypeScript would tell us an error, because now it's saying that it could be an application, and that's not assignable to type never. But if we cover all those cases, then what's left here is this is now of type never, because we've covered all the possible things that this could be by covering these 2 cases of abstraction and application. It's called a disjoint union. So before we actually define our abstraction function, which lets us construct abstractions, we've got to do some substitution, because we're going to have to substitute our free variables in the body of our abstraction with bound variables. And we'll also use substitution later in the next video when we're looking at how we are going to actually reduce these expressions to do computation with them. To do substitution, we take an expression, we take some variable that we want to replace. Now, this variable can be either a free or a bound variable that we want to replace. When we're creating abstractions, we will replace the free variables with bound variables. And when we're reducing an application by substituting the argument, we're going to replace our bound variables with Lambda expressions. So the substitute is any Lambda expression. Actually, that should be a lambda or a bound variable. Variable bound, I think I called it. Now we're going to check if the expression is a string. Then we're going to say, okay, if it's not bound, which is to say if it's free, this is what we're replacing here. This is our expression is equal to replace now. We're going to put in our, we're going to only be able to do that if the substitute is a bound variable, because we can only replace free variables with bound variables. You can't replace free variables with arbitrary expressions. So that's just going to throw an error if you try to do that. That's mostly just for me to make sure I'm not going to introduce a bug into this program. But the important part of this is that if the expression and the replace are equal, we're going to return the substitute. So that's the actual substitution part, where we're switching in the substitute in place of the variable. Otherwise, we're going to just return the same expression. So if it's a variable, let's say not the variable that we're substituting, then we're going to just return the original variable that we started with. The other possibilities are, if the expression that we're substituting over is an abstraction, we're going to substitute into the body. So we're calling substitution inside the body. And if it's an application, we're going to substitute into both the function and the argument. So we're going to substitute across both. And that's going to cover all of our cases. Again, we do this nothing never trick to make sure that we've covered all the cases. And that's how that's going to work. Now we'll see in a moment how substitution works when we demonstrate this abstract function. So with abstract, we're going to take a free variable and an expression, and we're going to look inside that expression for all instances of that free variable and replace them with a bound variable. So first we get our parameter, which is a bound variable, and you can see it has that type there of the little circle on the side. That's because we passed in false to this var constructor. Then in the body, we're going to take the expression, substitute for the variable. So this is the free variable. So that's what's going to actually occur inside our expression before we substitute, is this free variable. That could be like x or y. And we're going to substitute in our bound variable, which has the same name, but is going to have this little circle on the side here. And then we just return that object with all the necessary properties. So let's see a simple example of this. So we're taking f applied to y, and we're going to, well, actually, first of all, that's just f applied to y. And now when we abstract over that expression, we get this. So we have f applied to x here, and now we have lambda x bound x with f applied to that bound x. Now I'll just show you if we change this to f instead of x. So now we're abstracting over f. We get this lambda f, and now it's f that's bound instead of x. And now just to give you a slightly more complicated example where we're doing some sort of nested stuff, here we've got, let's go all the way to the right. So I'll save that and we'll see the result. So here we've got on the right, we've got z and w. So these are just these last two arguments here. But then here we've got abstraction over x for apply f to x and y. So inside of these square brackets here, we've got f applied to x and y, and we're abstracting with x. And that's turning this x into a bound variable. But then we've also have another layer of abstraction here where we're abstracting over f. And that is this abstraction. So this is a nested lambda abstraction. And that's like sort of like a function with two arguments. That's how you do multi-argument functions, is you do nested lambda abstractions. And so we can see that both f and x are bound, but y is still free because we haven't ever done a lambda abstraction over y. And finally, we're applying x to this whole thing. And that's what we're doing here. So you can see that works pretty well for constructing lambda abstractions. And in the next video, we're going to look at how we actually compute with these things, because as it turns out, with just this simple means of expression, you can create a functional programming language which can do any kind of computation. So one of the things that Church famously proved is that the lambda calculus is able to compute any computable function, and it's equivalent to a Turing machine, a universal Turing machine. So essentially anything you can do on a computer, you can do with this lambda abstraction, which is pretty remarkable because it seems like a fairly simple language, and yet it has this power to be able to do so much. So on that note, I'll say goodbye, And please comment, ask any questions. If you noticed any mistakes, please let me know. Please let me know what you liked or what you might like to see in future videos. And please like and subscribe. Thank you very much.